All right, so here is the data, promised data. Make it a little. Okay. So this is data for water vapor, so gaseous water. It's for 1 mole of water. And what this is it's data for how pressure. So here's pressure here. Pressure, it's in bar. Notice this is liter bar per mole Kelvin. The pressure is in bar, so that's why we're going to have to use this value of R, and the measured volume. Okay, and let's see. And so what is done in this experiment is that a mole of water vapor is heated to 473 Kelvin, so that's 100 degrees above water's normal boiling point. And then the sample is compressed. And that, of course, increases the pressure. And of course, the volume decreases. And what is done is the actual pressure is measured here. And, you know, the measured volume is very easy to measure because it's just the volume of the container. So it starts out at a very low pressure. This is, I'm going to number these 1 through 7. And ends up at an extremely high pressure, 800 bar. Okay, so what I'm going to do, if this was in class, I would have you do some of these calculations. So there are 2 things that have to be calculated. You have to calculate the ideal pressure. Now, what is the ideal pressure? It's simply nRT over V, and since n equals 1, it's really just, yes, it's just RT over V. Yeah, so then what you're going to do is you're going to take the actual pressure, which is P, and divide it by P ideal to get the compressibility or the compression factor. So I'll just do the first one, and, you know, maybe like the 5th one. Just do a couple of them. If you were in class, you would be, you know, doing some of these on your own. So it's nRT over V, or just RT over V, since n is 1. We have to use 0.08314 liter bar per mole Kelvin times 473 Kelvin. So the numerator is the same for all of these calculations. And we're going to divide by the volume, which is 393 liters. And when you do that, you arrive at the ideal pressure. So we're using this equation here. And it comes out to 0.1 bar. So the ideal pressure is the same. These 2 numbers are the same. That's really very, you know, that's really reasonable because we're at a very low pressure. So the ideal gas law holds at this low pressure, okay? When we take P over P ideal, of course, we get 1, right? And Z is 1 when we have an ideal gas. We do another one of these calculations, and then I'll fill in all the results. So if we go a little further down, let's say to number 4, okay, so now the pressure is 50 bar. That's the actual pressure. The ideal pressure, again, is nRT over V. So that's 1.08314, 473 over, now the volume is 0.607. Okay, and so that comes out to 64.8 bar. So that goes over here. Oh, it's number 4, not number 5, sorry. So now when you take P over P ideal, the actual pressure is only 50.0. I missed a sig fig, 64.8. And this comes out to 0.772. So you could see that the Z has decreased, and that's what we expect at moderate pressures. For water, 50 atmospheres is actually a pretty low pressure to start having these deviations from ideality that start pushing the that make the real pressure lower. And that's because water has a lot of intermolecular forces. So it starts being non-ideal at a relatively lower pressure than for some other gases. So now let's look at number 7, and 7 is really quite dramatic. Okay, so nRT over V, this is P ideal, is 1 again. I don't have to put the 1 in every time. Times 473 over 0.182, and that's 216 bar. So now P over P ideal is 800 bar, because that's the pressure here, over 216 bar. And we have a dramatic shift in what's happened. Okay, and I'm going to fill in some of the rest of these things. Let's see, so we have 10.4, sorry, 1.01, 0.994. So you could see here is where here's your kind of low pressure region where you basically have ideal behavior. Here is kind of your moderate pressure region. And here you start the high pressure region. Okay. All right. So what happened there? We were going along, and the pressures, the ideal pressures were always greater than the real pressure. So P was less than P ideal. And suddenly for this one, we have P is much greater than P ideal. So what happened here? Okay. So what goes on at 800 bar for water vapor? So what we have is at number 7, at 800 bar, we have P much greater than P ideal. And so it makes the Z greater than 1. Okay. So what happens is at high pressures, gas molecules are now extremely close together, are very close, certainly for a gas. And what happens is we get electron clouds start to overlap. And then when they get even closer, the nuclei tend to get close. Now, when electron clouds overlap, it's not quite as serious, right? Because electrons are all spread out in a cloud. But if nuclei start to get close, each one has quite a number of positive charges. So the repulsion is enormous. And I guess I could summarize this by saying that 2 molecules cannot occupy the same volume, same space. Okay. And so what happens is that the pressure goes up really quite dramatically. And so in this high pressure realm, we have pressures that are greater than the ideal pressure. So P is greater than nRT over V. So PV over nRT will be greater than 1. Okay. So we say that the gas is less compressible than ideal because it simply has a higher pressure. It has a higher pressure than the ideal gas law would predict. Okay. So we have this situation which I could kind of express in a graph. If you look at what happens to the compression factor or the compressibility, here, Z plotted on the y-axis versus pressure. So at first we have Z equals to 1. And it stays near 1 for a while, but then it starts to dip down to numbers that are less than 1. And then finally it goes up and can continue to go up. So this is what I would call the low pressure region, like over here. And then we have the moderate pressure region and the high pressure region. Over here, of course, we have the fact that the gas is ideal, that Z is very close to 1. At moderate pressures, now this is where attractions dominate. And you have to remember what's going on here is that it's the distance between the particles that's changing. Here we have very large distances between particles, so large distances apart. Here we have, a few molecular diameters. So maybe a few to 1 or 2, okay? And here now we have, well, let's call it a few. And here we have repulsions dominate. Because the molecules are just simply too close. Get out of my space, These attractions, what are they? They are the typical intermolecular forces that you have between molecules. You could have dipole-dipole. You can have dispersion forces. You can have hydrogen bonding. And of course, it wouldn't always be over the same distance that maybe hydrogen bonds in liquid water, for example. Those probably would be closer than a lot of the ones in here, but this still would be called hydrogen bonding. If you remember, dispersion forces are those, if you have a dipole on one molecule, it'll induce a dipole on another molecule. So it's kind of like if you had sort of a shift in charge so that you have more of the electrons on one side and more of the positive charges on another. This will induce a neighboring molecule to shift in a similar way so that you have an attraction here. And that's the temporary forces that I mean, that are dispersion forces. Of course, dipole-dipole forces is if you have literally a dipole, you have a delta positive and a delta negative on a molecule, let's say, and then another molecule next to it could line up the opposite way, and then you'll have these attractions. So for example, HCl would attract to another HCl. Something like that. And hydrogen bonding, those are the special dipole-dipole forces between when you have an oxygen, a nitrogen, or a fluorine on one atom that can be attracted to a hydrogen on another atom that itself is bonded to an O, N, or F. So these are, you have to watch out for the O, N's, and the F's. Those are the only atoms that can have these hydrogen bonds between them. Okay, so anyway, so I showed you this graph. This is the graph of our data that I just gave you. So these are the numbers that we calculated here. And what I've done here is I've taken this data and I fitted it to a polynomial in P. And you could see here's a constant term, and then there's a coefficient multiplied by pressure, a coefficient multiplied by P squared, and a coefficient multiplied by P cubed. So in general, we call these coefficients, these B prime. Don't worry why we call it B prime and not B. There's a reason, but it's not important. You can actually use more terms than this. And what you would do is you this is called a nonlinear fit. So you would actually find these coefficients that lead to the best agreement in the sense of minimizing that chi-squared, the sum of the squares of the differences between the points and the fitted curve. So if you remember now, and we have numbers here, right? Our B prime is negative 0.0049 for this set of data. C prime would be 7 times 10 to the negative 6, D prime 4 times 10 to the minus 9. And all these have crazy units because all together, they're the units of this times a unit of P cubed will have to be unitless because Z is unitless. So they have crazy units, but we don't worry about that. Okay, so if you look at this Z is actually PV over RT. It's actually PV over nRT, but N is 1, so we don't have to worry about it, right? Because this data was for 1 mole. So it's 1 plus some coefficient times pressure, and these would be known after you did the fit. Let's say it goes out to that term there. If you look at this equation right here, you see that it is a relationship between P, V, and T. So it is an equation of state. And we call it the Virial equation. But, don't kid yourself. It's not like the ideal gas law. It's an equation of state, but it required a ton of data. So finding the Virial equation requires a ton of data. And you need to have that ton of data for every temperature. So you can't just say, I'm going to find the Virial equation for water. No, I'm going to find the Virial equation for water at 473, at 430, at 453, at 462, at all different temperatures. You have to get different data. So finding the Virial equation requires a ton of data, and you need to get that data at each temperature. So it's really a lot of work, and it's not an equation that you could just write for any particular gas. It's different for each particular gas. It's not the same for all of them. So you need tons of data, and you get this thing called the Virial equation. These things are called the Virial coefficients. Even this one is called a Virial. It's the first Virial coefficient. This is the first Virial coefficient, the second Virial coefficient. Okay. And if you look at it, it's really not very intuitive. Like if you compare it to the ideal gas law, P is nRT over V. That tells you P is proportional to 1 over V if you hold the temperature constant. P is proportional to T if you hold the volume constant. P is proportional to N. There are these nice, simple, intuitive relationships. Not so with the Virial coefficient. It's not very intuitive at all. You really cannot look at this equation and see what the relationship is between P, V, and T. You could, if I give you a pressure, you could, how would you do that? Right, Z, you could calculate Z if you had these pressures, and then you could say figure out the volume if you knew the pressure, because Z is PV over RT for 1 mole. So V would be ZRT over P, okay? So if you knew the Z, right? If I told you these coefficients and I gave you a pressure, you could calculate Z. You know the pressure, you could calculate the volume. But there's really there's nothing intuitive about it except for one thing. And here's the one thing, which really isn't much. Okay, so the one thing is that this Z is that in the limit, as the pressure goes to zero, remember we have, I always said from the beginning that the ideal gas law is a limiting law, which means it's not valid at all pressures. And now I've shown you what indeed happens at all different pressures. It's a limiting law, but you could see here that as the pressure goes to zero, right? So this is going to go to zero. Well, what you're left with is that Z equals 1, and that's ideal behavior. Okay, so I didn't lie to you. There's merit that you can see right away to this equation, but it really doesn't. It's basically does not satisfy you any intuition. So is there a better equation of state? More intuitive anyway. For a real gas. Oh, and I don't want to put down the virial equation. I do want to mention something else. And that is that the values of these coefficients, B prime, C prime, D prime, for water anyway, gaseous water, at many temperatures are tabulated, well known. And they have to be, right? Because if you happen to be an engineer that have to deal with, you know, high pressure steam, you better know what the properties of that steam are. And the way you would know that is, you know, is to use the virial equation, the published coefficients for whatever temperature you're interested in for water. And these are basically CRC type data. You could find them online, or you could find them in those old CRC handbooks. But anyway, there is a better equation of state, well, better in the sense of being more intuitive, and that's called the van der Waals equation, which is going to be a start next time's class. So that's it for now. Stop this recording.